Hello everyone, welcome back to the latest lecture session. In the last couple of sessions, we started discussing about how to remove those bivalent cations which lead to hardness, calcium and magnesium, right? In that context, we looked at some acid-base related background, acid-base chemistry, understood that we have equilibrium between the acid and the base, and the key aspects which decide the ratio of the acid to the base are the pH and the pKa. pKa is the acid dissociation constant, and again Ka, which is pKa, which is minus log Ka, right? What is Ka? Ka is that equilibrium constant for that acid dissociation reaction. So we also looked at equilibrium constants and how to write that, right? So quick recap and then let's go forth. After discussing these aspects, we started discussing about carbonate hardness. So this is referred to as temporary hardness, and the insoluble when heated they tend to form deposits and such, but again temporary hardness, let's say, right? Those that are associated with carbonates, yes, that's something we discussed. Non-carbonate, obviously we call that as permanent hardness. Again, this is a working understanding, I guess. It's not removed when the water is heated, fine. So non-carbonate hardness is total hardness minus the carbonate hardness, yes. So this non-carbonate hardness, obviously as the name indicates, non-carbonate, right? This is when the relevant ions, calcium or magnesium, are associated with ligands other than HCO3 minus or CO3 2 minus. So non-carbonate hardness. In that context, we looked at the figure. So here we looked at different permutations and combinations. So carbonate hardness, it's equal to the alkalinity, right? In this case, because alkalinity is less than the total hardness, yes. And what do we see here? We also saw that, or we came across this aspect, alkalinity is equal to the acid that's required to bring down the pH to 4.5 or 4.3. That's the actual practical definition that is given in the standard methods when we try to, find the alkalinity by titration. So considering that the bicarbonates or the carbonate system is the only system that's prevalent here in this water, so we list all the bases that can neutralize the acid, right? Plus HCO3 minus plus 2 times CO3 2 minus. Why 2? Because as you can see, CO3 2 minus can neutralize 2H plus, and obviously minus H plus, right? We are adding the acid H plus. So as we see from or near about pH 7 and looking at the speciation diagram, we see that there will be little to no CO3 2 minus present. OH minus and H plus will cancel out each other when the pH is near neutral. So when we talk about alkalinity, it is typically HCO3 minus, especially when the pH is near neutral, right? But be careful when making this assumption, let's say, right? Because let's say if people want to ask questions and throw you off track, this is obviously one particular case where people try to throw you off track, right? That alkalinity is not equal to HCO3 minus, but it depends upon the relevant scenario. So if not, you will have to calculate the alkalinity like this, and alkalinity here, the units of the relevant compounds here are moles per liter, right? And the units will be in terms of equivalents per liter for alkalinity, let's say. And then we moved on to looking at different permutations and combinations if total hardness is greater than alkalinity, right? And then carbonate hardness will be defined by the ones associated with the carbonates, right, meaning alkalinity, and non-carbonate hardness will be the difference. And for the total hardness being less than alkalinity, then all the hardness will be only carbonate hardness. Same case, we looked at differentiation with respect to calcium carbonate hardness, calcium non-carbonate hardness, and so on and so forth, right? This we already discussed, so I will move on. So here you see lime being added, right, or slaked lime anyway, or hydrated lime. So as you see, it forms, this is the belt, weighing belt, and depending on the mass required, you are going to add it to the slaker tank, let's see, right? So again, it's a mass balance which we will look at later. And here the lumpiness, right, you see the lumps. Yes, you see the lumps, that's why they form cakes. So obviously even when you are trying to measure something with a spoon or such, if it forms cakes or lumps, it's difficult to measure, right? So again, that's what I guess they are trying to say, and it inhibits the flow out of the silo, let's see, right? So that's something to keep in mind. But this is for lime or hydrated lime. And with soda ash, which we will also look at later, we are always talking about lime, soda, softening, right. So, lime is typically hydrated lime, CaOH twice, I guess, and soda or slaked lime, pardon me. And soda, when we say soda, we are talking about Na2CO3 or soda ash. But soda ash, unlike lime, you can see the texture, right, and it's relatively powdered, and it's thus easy to, what do we say, dissolve or weigh and dissolve, let's say, right. So, that's something to keep in mind. So, here it's granular and thus flows easily, right. That's one thing to keep in mind. Well, just a practical aspect I wanted to mention based on the information that Mackenzie Davis student presentations gave. These student presentations are accessible to you too. You can just look up the link from the Mackenzie Water and Wastewater book and access a variety of such what do we say, practical pictures or pictures which convey practical information, right. Let me move on. So, what's the approach here, right? As in, I know that I have Ca2 plus and Mg2 plus, and some of these will be associated with either HCO3 minus or CO3 2 minus based on the pH of the system, obviously, and some will be associated with those that we refer to as permanent hardness or such, let's say, right. So, how do I get these out of my relevant system? We will look at other ways, but here we are talking about precipitation and then removing the precipitate from the relevant solution. So, precipitation, what is it that we are trying to do? These compounds are now dissolved, calcium and magnesium are dissolved in water. Depending on the conditions that you create, depending on the ligand that you add, ligand electron rich, metal or such, calcium, magnesium, electron poor, let's say, right. Again, depending on the pH conditions and the relevant compounds, you can see to it that the solution is supersaturated with respect to a certain kind of solid, and then you can see to it that your solid precipitates out. So, when the solid precipitates out, it is not dissolved anymore, right. Again, size is obviously bigger, and then you can look at coagulation and flocculation and then sedimentation or such to remove these suspended matter from your water. So, the approach is, we have something dissolved, we want to precipitate it out so that they are not dissolved anymore, but become suspended solids or that can be settled out, right. So, that is the approach. So, here I have to precipitate them out, right. So, typically I will try to precipitate calcium out in the form of calcium carbonate, the solid, and magnesium hydroxide, the solid. Again, different forms of calcium or different other compounds are feasible, but based on what is typically available in water and what is easy to dissolve. So, this is what people have been using, this meaning these are the solids that people prefer to precipitate out, CaCO3 and magnesium hydroxide. So, do I have the figure? Okay. So, one aspect I wanted to mention here is, so what is the solubility product related equation here, right, or dissolution, let us say CaCO3. If I write the equation as dissolution, Ca2 plus CO3 2 minus, right, and for this it goes to, it can dissolve into Mg2 plus and 2OH minus. Again, S is for the solid, obviously these compounds, other compounds are dissolved now. So, they are in equilibrium, right, in general saturation, supersaturation, nucleation, agglomeration and such, but we will not go into that. There are more aspects to understand, but here let us just look at the bigger picture. You need to saturate it, right, or supersaturate it rather. So, for the reaction to go from the right to the left, what do I need to do? Le Chatelier's principle, or in general, what do I need to do? If the system is at equilibrium and I want to trigger precipitation, what do I want to do? I want to saturate or supersaturate the solution with Ca2 plus or and CO3 2 minus, right. So, when I increase the concentration of these particular calcium and CO3 2 minus, the reaction as written will then try to shift towards the left and the solid will precipitate out. Same case here, if I increase the magnesium concentration or increase the OH minus concentration, meaning increase the pH, then the system will try to go left so that it will achieve a new equilibrium and then the solid can precipitate out. So, here we can either increase calcium or magnesium, that is one thing. But here we are talking about removing the calcium or magnesium that's already in solution, right? Adding more calcium again doesn't really come into the picture here, but we will look at that. That's an internal aspect here. So what else can I do? I can increase the CO3 2 minus or increase the OH minus. How do I increase OH minus? Obviously for that I can increase the pH. pH is negative log H plus, right? And H plus plus OH minus, they will be in equilibrium with water, right? And again, I guess I should have written it the other way. Okay, let me write it this way. Yes. And water dissociation constant Kw is equal to 10 power minus 14. This is again like the equilibrium constant. So I'll have the activities which I am assuming to be the relevant concentrations. Concentration of H plus, concentration of OH minus, by activity of water. Activity of water, we are going to assume it's a dilute solution, so it's going to be 1, right? Kw, which is 10 power minus 14, is concentration of H plus into OH minus, right? So if I decrease the H plus concentration, OH will increase or such. You can see the relationship here. So I am going to have to increase the pH if I want to increase the OH minus concentration. So that's something to keep in mind. Approach 1 is to increase the pH, right? That's for magnesium hydroxide precipitation, right? I want the system to go in this direction. Fine, okay. So what about the other aspect? If I want this reaction to go in this direction, what do I do? One approach, as we discussed, was increasing OH minus. Here we are trying to go and increase CO3 2 minus. So if the water does not have any CO3 2 minus or HCO3 minus, then I will think of adding, what do we say, bicarbonate or carbonate. But in general, water will have some bicarbonate or carbonate. Why is that? In general, water is in equilibrium with carbon dioxide typically, or has been in contact with some deposits earlier, and you are typically going to have some CO3 2 minus and HCO3 minus. This you are going to typically have. But from the speciation diagram, let me draw this here. So this is my speciation diagram. Yes. This is for HCO3 minus, the green one was for H2CO3, right? And this is for CO3 2 minus. Let me just write that down, CO3 2 minus, right? But the pH here, pKa is 6.3. So at around neutral pH, what is predominating? Mostly it is HCO3 minus, right? Mostly it is HCO3 minus. Maybe I should write that down in case people are still not clear. So the middle one corresponds to HCO3 minus, the one on the far left corresponds to H2CO3, the acid. So as you can see, at around pH 7, which I am representing by this line, we see that it's mostly going to be present as HCO3 minus. But I need CO3 2 minus. So how do I see to it that more of CO3 2 minus is present? If I just add some CO3 2 minus, maybe yes, it itself can lead to increase in pH. But as you see, if I increase the pH by different means, obviously at higher pH, CO3 2 minus will predominate. And what is this pKa? This pKa is 10.3. So near about 10.3 or such, you can see you will have relatively significant amount of CO3 2 minus. So by increasing the pH or by adding CO3 2 minus, right? So the second approach is, or the other approach for calcium removal is to add CO3 2 minus, or if there is already enough HCO3 minus, then increase the pH such that the ratio of HCO3 minus or let us say CO3 2 minus to HCO3 minus increases, right? Increase the pH such that ratio of CO3 2 minus to HCO3 minus increases. So this is the approach, one for magnesium, one for calcium. But again, what are the key aspects here? We need OH minus, which is typically present in water, and we will also need CO3 2 minus. So what are the different ways you can raise the pH and such? We will look at that later. I want to look at one figure for now, okay? So here we are trying to achieve precipitation, right? And let's look at it. So pH is on the x-axis, and on the y-axis we have log of calcium. This is a log C pH diagram, right? Log C pH diagram. Solubility of CaCO3 as a function of pH is given, and looks like the solubility product Ksp for CaCO3, which we discussed earlier, right? CaCO3, the solid going or being in equilibrium with Ca2 plus and CO3 2 minus. The KSP or equilibrium constant for this, which I am mentioning as solubility product. Why solubility? As you can see, the solid is dissolving. Solubility product will be equal to activity or concentration of Ca2 plus into concentration of CO3 2 minus, right, and that they are saying is equal to 4 into 10 power minus 19, and the total calcium total is equal to 2 into 10 power minus 3 moles or 2 millimoles, right. So, that is the information that we have. I am just writing it down so that you understand the background, right. So, with increasing pH, I guess here they are talking about calcium, the free metal, hopefully anyway. So, again let us see, at relatively low pH you need to have relatively high calcium free metal concentration, but as I keep increasing the pH, I see that even at relatively low calcium concentration, or I will be able to achieve relatively low concentration maybe, right, at around this pH or such, I can see that I will start forming the relevant solid, let us say, right. So, you understand the pH level that is required, and also you saw that pKa2 for the H2CO3 system is 10.3. So, you can also understand why this is the case, because at this case too you will have CO3 2 minus being predominant, right. So, that is one aspect to keep in mind, right. Same case here, where let us move on to the right hand side and let us look at this log C pH diagram for magnesium. And here solubility of magnesium hydroxide, the solid, as a function of pH, and the KSP is given. Please note that KSP is much lesser here. The solid line is for solubility in 23 waters, right, designed by Thomson et al, and we have it from Kittonen et al, right. Again, the solid line is looks like the average, let us say, of a few sets of data. So, what do we see here? As we increase the pH, let me write down the equation. Magnesium hydroxide, the solid, it will be in equilibrium with Mg2 plus and OH minus. So, as I increase the pH, what is happening? I am increasing the OH minus concentration. As I increase the pH, OH minus, so then you can see that magnesium hydroxide concentration starts, or magnesium hydroxide, the solid, starts precipitating out, right, and theoretical and actual seems to be lesser. So, in general, for this removal to take place, typical pH you want is around 11.5 or so, even done at 10 point something, but in general at around 11.5. And for calcium carbonate removal, let us say, or calcium removal in the form of CaCO3, typical pH is around 10.5, typical, again keep that in mind. So, this is where it comes from. So, now that we have the information, let us see how we are going to go about it. So, I know that I have calcium, I have magnesium, and I have what else? I can have HCO3 minus at around pH. I am assuming the water is around 7 or 8, and thus all the CO3 2 minus is present as HCO3 minus. And then I will have other ions which are of not great interest for me here, but I am mentioning that because that indicates that some of the calcium and magnesium is or can be associated with non-carbonate hardness, right. I might not have enough carbonate for everything. So, let us see how to go about it. So, different ways to raise the pH, as in we mentioned that we can either raise the pH, or for calcium increase the CO3 2 minus concentration, and even for this, rather than adding CO3 2 minus, if there is already enough HCO3 minus, we can increase the pH, right. So, approach resolves around adding a compound that will increase the pH, and if required add CO3 2 minus to the system. So, that is something to keep in mind. So, typically we can add lime, CaOH twice, relatively cheap, hydrated or slaked lime, pardon me, and this, as you can see, it will immediately dissolve to Ca2 plus and 2 OH minus. Though I write this equation, it is typically an irreversible one, if not irreversible, mostly in this direction, it will dissociate into Ca2 plus and 2 OH minus. But here the question that should arise is, fine, I am increasing the pH by adding this OH minus, but seems like I am also adding a source of calcium, and that seems to be counterintuitive, isn't it? I mean, I want to remove calcium and magnesium, but I am adding a source of OH minus to increase the pH that also has calcium. Well, that seems counterintuitive, But if you look at the stoichiometry, it's not as difficult or as counterintuitive as we would expect. So, first aspect, to increase the pH, we are going to add the CaOH twice, let's see, which I am going to refer to as lime. So, from this I am going to get Ca2 plus and OH minus, right. So, first thing is, if there is any acid present in the relevant system, that will consume the relevant OH minus that I am putting in. So, whatever I have, typical acid can be CO2 in equilibrium with water. When we say CO2, it is almost always present as H2CO3 in the water, let us say, right, CO2 aqueous. But if I add any OH minus, the first consumption or the consumption of OH minus will be by CO2, right. So, that is something to keep in mind. OH minus will be consumed by the CO2 or H2O CO3 as you write it, right. So, whatever I add OH or lime first will, if there is any carbon dioxide or H2CO3 present, or if there is any dissolved carbon dioxide present, it will consume the OH minus first. That is one thing to keep in mind. Once I have seen to it that all the acid, right, this is an acid H2CO3, and that I am quenching by adding OH minus from my lime, fine. So, the additional lime that I am going to add, let us see what that is going to happen. I know that by adding lime, what am I getting? Ca2 plus plus 2 OH minus. But in the water, what is already present? I already have some lime, and let us say I have some HCO3 minus, let us say, right. And I guess if you look at the stoichiometry, this OH minus, right, I am increasing the pH. So, when I increase the pH of the water, this HCO3 minus is going to convert to CO3 2 minus, right. We know the speciation diagram, we already have that, but I will just write that here for the sake of understanding, let us see, right. I mean, let me find, this is for HCO3 minus, HCO3 minus, x axis is pH, y axis is the relative concentration or such, and the last one will be for CO3 2 minus, CO3 2 minus, right. And this is going to be, this pKa2 is around 10.3, right, and this pKa1 pardon me is 6.3, right, around that. Let me also write down this particular aspect, it is H2CO3 here. So, when the pH is around 7, as you can see, most of the CO3 2 minus is present as HCO3 minus, but by adding OH minus, you know, the equilibrium is going to shift between H2CO3, HCO3 minus and CO3 2 minus and go towards CO3 2 minus. And once you have enough CaCO3, we know that we have this equation, right, Ca2 plus plus CO3 2 minus can precipitate out as CaCO3, the solid. This reaction will be favored, especially when you have higher CO3 2 minus. So, you will have 2 CaCO3 being formed. So, in effect, even though I am adding some calcium from the lime, I am still removing 1 mole of what do we say, calcium, along with the mole of calcium that I am adding. Obviously, that is not balanced, but we will look at the balanced equations later. So, this is one aspect, but key aspect to note is that this will occur only if there is already some HCO3 minus present in the water. If not, we have to add the HCO3 minus, right. Okay, fine, that is one aspect. So, if what about magnesium or such, let us see, I know that magnesium hydroxide will precipitate out as, or magnesium will precipitate out as magnesium hydroxide, right. So, how will this come into the picture, or how will this be done? So, I already have magnesium, right, and if I am adding the relevant calcium hydroxide, what am I adding? Lime, right. What will I get? Ca2 plus and 2 OH minus, right. This is what I have. So, what is it? I will end up, what is it now? Removing this particular magnesium hydroxide, right. I should have written MgOH twice, the solid there. Let me just write that down, magnesium hydroxide twice, right, or MgOH twice. So, for this to occur, obviously Mg2 plus is there, 2 OH minus, fine. But as we know, and we looked at from this previous equation, for this to occur, we have to increase the pH such that the pH comes to almost around 11 or above 11, let us say. That is something to keep in mind. But if you look at the stoichiometry, it will come to that more or less in general, let us say. But what else will happen here? If there is no alkalinity or no carbonate left, this Ca2 plus will now be introduced in the system. So, in effect you are removing magnesium, but adding calcium, let us see. But if there is alkalinity present or carbonate present already in the solution, then this calcium will combine with that and be precipitated out as CaCO3, the solid. So, what happens will depend upon the amount of carbonate or such that is initially present. So, if you have enough carbonate and this is magnesium carbonate hardness, then this is going to take place and not this, let us say, right. So, that is something to keep in mind. So, what about other aspect? What about magnesium that is not associated with what do we say, carbonate hardness? So, then obviously you are going to see to it that the other reaction occurs, let us see. If it is Mg2 plus and it is associated with other what do we say, compounds which are not carbonates. So, what will happen here when I add lime? Ca2 plus 2OH minus plus this. So, that will have magnesium hydroxide, the solid precipitating out, but you will now add calcium, let us see, right. Let me erase the other part from here so that there is less confusion, and I will write it up such that there is lesser or greater clarity here, right, plus CaCO3, the solid, right. So, again it all depends upon whether I have whether it is magnesium carbonate hardness or magnesium non-carbonate hardness. So, here at the end of this picture you see that I still have some calcium, I am introducing calcium, in effect I am introducing some calcium, right. So, how do I remove this calcium? We know that calcium will be removed only when there is enough CO3 2 minus here, but I have already used up all the CO3 2 minus looks like in the system to either remove it in the remove or precipitate CaCO3, the solid. But for magnesium non-carbonate hardness and such, I am adding calcium in the source of from lime, and that is still there. So, how do I remove this? Or even if there is any calcium that is present as non-carbonate hardness, what have we removed until now? The CO2, the calcium carbonate hardness, and what is this? Magnesium carbonate hardness, and here we have removed magnesium non-carbonate hardness, right. So, this is what we have, but how do I remove calcium non-carbonate hardness and also the calcium that I have added during this particular stage? How do I remove that? I will remove that by adding a source of CO3 2 minus, and what is that source of CO3 2 minus? That is going to be my soda ash, right. So, this will have to be added either here, or if there is enough alkalinity, fine. If not, I will have to add it here too, right. So, depending on where we add it or such, the stoichiometry will change. If you are assuming that okay, this is magnesium with carbonate hardness, I do not need to add it here, but magnesium due to non-carbonate hardness, and if I want to remove calcium right here, some people will add lime here itself, not lime, soda ash. What is soda ash? Soda ash is nothing but Na2CO3. So, this will have to be added when I want a source of CO3 2 minus. So, soda ash is typically added here. Why? Because this I do not want this free calcium to stay in this solution. If I added soda ash here, right, along with lime, I would have precipitated out this calcium. Same case with calcium non-carbonate hardness. Let us say I have calcium that is associated with non-carbonate hardness, and what will I do? I will add soda ash, let us see, right. Let me add the soda ash. So, that is 2 times Na plus and CO3 2 minus, right. So, I am adding that soda ash, and then I am going to have Ca2 plus, not Ca2 plus, CaCO3, the solid precipitating out, right, and the other ions obviously. So, where am I adding soda ash? To remove calcium non-carbonate hardness, and also in this magnesium non-carbonate hardness to remove the calcium that is coming from the lime. So, in 2 aspects I am typically adding the soda ash, let us see, right. So, that is the relevant aspects. These are the 5 or so steps that you can think of, and if I missed anything in general, we will look at them later, but that is the approach, and we will now look at how to be able to calculate different variables and such, or the dose of lime from an example, but we will look at that later. And thanking you for your patience. That's it from me for now.